9. On Thursday, we begin 10. And so the week after that, we'll finish up 10. And the week after that, we'll have an exam. All right?
So low oxygen classes?
Yeah.
Okay.
Okay, so let's get started. You guys see that? You see that? Is that okay? So the stuff that we're going to start talking about right now, oops. The math that we're going to start putting together right now all kind of refers to stuff that we already talked about. And what we talked about was ions going in solution and the kinds of things that happen to them. So we did those derivations where we looked at the energy required to form a point charge inside a solution as a dielectric constant that's different from the dielectric constant of vacuum. We showed that due to the energy and relative energy of the charged species in something that has that different dielectric constant, that it's lower energy overall. And so we showed that the chemical potential of an ion goes down when it's in a dielectric media. We also talked about how ions in solution interact with each other, and when they do that, they have kind of electric or potential minimizations. They reach a potential minimum when they're allowed to interact with each other in solution. And so these are both effects that tend to lower the chemical potential of an ion when it goes in solution. So in general, we expect chemical potentials of ions in solutions where there's favorable interactions with the ion, like in water, to be lower. So real quick review. Let's go back to our derivation of the chemical potential of things in solution. We had that the chemical potential of a substance, of a solute, not a solvent, but a solute, went as some standard or some reference chemical potential plus the correction, and the correction went as the mole fraction. And for dilute solutions, the mole fraction is proportional to the concentrations. The mole fraction is equal to the concentration times some multiplier C. The brackets there on the B is to indicate concentration. And so you can express the chemical potential of an ion or a solute as mu naught plus RT times natural log of concentration over the standard concentration. And this mu naught term here is meant to say that we've added to mu star this RT line C, where C is whatever multiplier is necessary to make that transition from mole fraction to concentration units. Okay. So take-home message: chemical potentials of solutes are expressed as a function of the concentration. That law that we put together talks about ideal solutes. And so ideal solutes are solutes that obey Henry's law. Henry's law kind of assumes that there's uniform forces holding that solute particle into the solution, and that those forces are similar to the forces around other molecules. But for ions in solution, we saw that the forces that bind that ion are stronger because they're the electric forces. When you have a positive ion in solution, the negative pole of water orients towards it. When you have a positive ion, when you have a negative ion, the positive pole of water orients towards it. And so we know that this simple concentration dependence relationship that we derive up there is not necessarily going to hold, but we can keep the math. Damn it, I'm just not very good with technology. It's not supposed to happen. Stop it. We can keep the math that we used here, this guy, if we correct it by multiplying it by some coefficient, by multiplying that concentration by some coefficient. And that coefficient is whatever it needs to be to account for the actual energy of that ion in the solution, in the species, right? So with that, our amended form of the chemical potential is some chemical potential of a reference state plus RT times the natural log of concentration times whatever that coefficient is. And that coefficient is going to be referred to as an activity coefficient.
Find that. I was angry.
Damn it, did it again. All right, this is not my fault here.
We'll blame Alex.
I was doing it last.
Damn it.
Can you see that?
Eh.
For some reason, it's not letting me scroll. It did it
Why don't
just.
you just make it into a screen?
Why don't I what? Make it for. If you do it with the full screen, it still won't let me scroll up and down. It was letting me do it 2 seconds ago.
Did you try using the arrows?
There's no arrows.
Like
No,
on
your
the keyboard.
your keyboard arrows.
Maybe you could try like clicking and dragging.
Pretty?
Yeah, exactly.
Pretty?
I think that's what he's doing.
Pretty?
Yeah, I was trying to click and drag, and it's not. The arrows aren't working either.
What is that?
All right, this is stupid. This keeps me from giving a lecture.
Time to go home.
Squeeze it.
Okay, there. Jesus H. Okay. I hate when technology works one way with 1 second and then it stops doing what it was doing before. Next, it makes guys like me really confused. So anyway, if the chemical potential of the solute is higher than you would expect for an ideal system, for a system that obeys Henry's law, then that activity coefficient is going to be greater than 1, right? If the chemical potential is lower than expected for something obeying Henry's law, then that activity coefficient is going to be less than 1. If the solute is behaving according to Henry's law, the activity coefficient is going to be equal to 1. Yeah? So for an ion in solution, we said that it's bound more tightly. This lowers its chemical potential. This means that relative to something that obeyed Henry's law, when it's the concentration, we would expect that the chemical potential was lower for that ion in solution. So what would the activity coefficient be? Greater than, less than, or equal to 1 for a system like this? Okay, so we're talking about activity coefficients, right? And we said that for real systems, we have to correct our chemical potential term, that the Henry's law chemical potential, which one is concentration, by using some activity coefficient to multiply that concentration term to account for how the chemical potential of our system varies from an ideal system, right? Now, I said that ions in solution, because they have charge, are going to have lower chemical potentials, right? Lower chemical potentials means that this whole term needs to be smaller than it would be for a solute obeying Henry's law, right? Because this ion is bound by stronger forces to the solution. So in that case, if we want a lower chemical potential by comparison to Henry's law solutes, what would this coefficient have to be? Greater than, less than, or equal to 1?
Less than.
Less than, right. So that's what I was getting at. So for these ions in solution, you expect that that activity coefficient is going to be less than 1 because the ions in solution actually have a lower chemical potential. We're talking about aqueous solution. Generally, they have a lower chemical potential. All right, next picture. Oh, sorry, one last thing. It tends to be that systems as they go towards infinite dilution, ionic systems as they go towards infinite dilution and other systems, because solute-solute interactions are minimized. In the extent of infinite dilutions, most systems obey Henry's law. They behave ideally in that sense. And so we have the tendency that as the mole fraction or as the concentration of a system goes to 0, the activity coefficient becomes closer and closer to 1. And 1's what the activity coefficient would be if the system were behaving ideally. So when you see that in your book and they say as concentration goes to 0, activity coefficient goes to 1, this is because systems obey Henry's law on the limit of infinite dilution. See, it worked that time just fine. Just click and drag and boom, and it did it. 10 times 2 seconds ago, it wouldn't work. I don't get it. Okay, so there's a problem with ionic systems, and that problem is that when you're measuring the energy changes in the system of ions, you're never measuring the effects of one ion at a time. Ions always come in pairs, right? Salts are neutrally charged. So if you've got a copper 2+ ion, then it's coming probably with 2 chloride ions. And when you dump the copper 2+ ion into solution, you're dumping a couple chloride ions in, and you measure any heat exchange or work that can be done by that system, and you're not really just, you're measuring the effects of both ions. And so what this does is it kind of invites an average activity coefficient, and that's what gets used for describing these ionic systems, is these things called average activity coefficients. We're going to show you how they're derived here in just a second. Let me just look and make sure I covered everything. So we discussed that. We discussed that ions being at lower potential due to hydrating waters and favorable interactions with other ions in solution. Okay, so we already covered everything that's on here. Move down a little bit. So our average activity coefficient, we're going to call it plus minus. I don't know what the name of that symbol is. Is that mu? It's mu plus minus?
Gamma.
Gamma plus minus. So gamma plus minus ends up being equal to, for a 2-component system, and it's changes for other systems. Gamma to the p, gamma plus to the p, gamma minus to the q, to the 1/s power, where s is p plus q. And p and q are the coefficients in front of each ion in the system. So if you have something like copper chloride, and copper is your plus ion, and there's 1 copper, and so p is going to be 1. And if you got 2 chlorides, you got 2 Cl minuses, so q is going to be 2, and s is going to be 2 plus 1 is 3. So basically, what you do is you take the activity coefficients and you raise them to the power of the coefficient in front of the ion. The coefficient that tells you how many ions are generated in solution when 1 mole of the thing dissociates, 1 unit dissociates. And you take that to the 1/s power, where s is the sum of the powers that you raised everything else to. We're going to see, look right now at the derivation. So to see where this comes from, this is in your book, you can go back and take a look at it. We can write out the chemical potentials of, this is assuming that we have just 2 species in solution, positive charged species and the negative charged species, and the chemical potential is going to be chemical potential naught, RT natural log of the activity coefficient times the concentration divided by C naught, where C naught is just going to be equal to 1 because it's your reference concentration. You write those chemical potentials out, and you start separating the terms. And those natural log terms can be separated relatively easy because log of something times something is the same thing as the log of that thing plus the log of the other thing. And so these terms, RT natural log of gamma times concentration, can be separated and turned into RT natural log of gamma plus RT natural log of concentration. We separate those guys out, and then we put the terms with gamma back together in one term. And so we have then a thing that looks like the total Gibbs free energy for a Henry's law solute, something that's behaving ideally, plus this correction term that accounts for the non-ideal behavior. This basically looks like ideal system, and we add to it this correction just to bring us back to where we started. If these things are less than 1, natural log of something that's less than 1 is what? Positive or negative? It's negative. And so this correction is going to be lower. It's going to lower the chemical potential relative to what the ideal chemical potential is. So then we just take this term, this gamma plus times gamma minus, and we're going to say we want to calculate the gamma average. And so we say that this is not necessarily gamma plus times gamma minus, it's the average gamma squared. We take that term and we slap it back in here into the equation, and then our chemical potential looks like this. We've got this RT natural log of something to the second power, but that's the same thing as saying 2 times the RT natural log of that thing that had been raised to the second power. And so now we have this term. That term can be pulled apart into RT natural log of gamma plus minus plus RT natural log of gamma plus minus. So we can pull 2 of these out. We sub them back into the chemical potentials of the ions, the original ions that we had, and we get these terms where the chemical potential of the positive ion is its ideal potential plus RT natural log of gamma plus minus, and the chemical potential of the negative ion is its Henry's law chemical potential plus that RT natural log of gamma plus minus. So basically what we just did there is we threw some math together to say that we can look at the total change in the chemical potential and then just kind of split the difference between the positive and the negative ion. Just assume that the total change in chemical potential, the total deviation from ideality was shared evenly by the two. And take a look at this. One last look at this equation. We're going to go over to the final product equation right now. So to get to our final equation, what we do is we take those terms that had RT natural log of the average activity coefficient, that gamma plus minus, and we shove them back into the log terms that multiplied the concentration. Just the same way we extracted them, we can put them back in. And so now we have an expression for our chemical potential of the system. The total chemical potential is equal to standard state chemical potentials of each ions plus RT natural log of what is now not the individual gamma for the species, but the average gamma times the concentration. That's a bit heady, but what I want you guys to remember is that essentially all of that math did was take the observed effects on the chemical potential due to the deviation from ideality of the chemical potential, and I guess assign an average effect of that change to each ion. Boy, I don't even know if it makes sense when I say that. Do you guys get that? I feel like I kind of said it in a stupid way, or in an unclear way. All right. So we have this new term for the chemical potential, and it goes as these activity coefficients.
So the real equation is 1 over p plus q, not 1 over 3. That.
Yeah, well, in a system where p plus q is 3, then it's you raise it to the 1/3 power, right? You're multiplying these things together, and you multiply 5 items together. You take the 1/5 root of that, and you get the average, right? Of the whatever. That's the kind of logic. So the next question becomes: is there a mathematical way to predict what gamma will be for an individual ionic species? So gamma will vary between ionic substances and non-ionic substances. We're focusing on ionic solvents right now. And it turns out that because the things that dominate the energetics of an ion in solution are the attractive forces between the ion and other ions in solution. So I always want you guys, at least those of you that go on to be chemists, to remember this equation. This equation, we see it a little bit during intro physics, and it really kind of gets lost in a lot of chemistry that comes after that, but I don't want you guys to lose it. That's why I keep writing it. This is the force that two charged species exert on each other when they're separated by some distance r, right? And although electronic wave systems don't act as point charges, and this is derived from point charges, the basic behavior is the same for both systems. You've got positive charge and negative charge, and they attract each other, and it's a really strong force. And for ions in solution, this is the dominant effect. So it's that force between ions that ends up affecting the chemical potential the most. And so you can actually end up deriving an equation or a term that expresses the ionic activity for a species, or the average ionic activity, in terms of the charges. These Z's are the charges on the ions. So if we're looking at copper chloride, the positive Z would be 2 plus, and the negative Z would be 1 minus, times the ionic strength. We'll talk about what the ionic strength is in just a second, and a constant that basically is a function of the solvent. So this A constant, different solvents have different abilities to communicate electric fields over distances. And so when you're looking at minimizations of potential, you have to account for how strongly those forces are exerted between ions. So A is a constant that talks about your solution. In aqueous systems, we're talking about water. So A is something that is specific to water in the case of aqueous systems. The ionic strength, we'll talk about more in just a second, is basically a measure of how many ions are present in the system. If there are a lot of ions in the system, if there's a lot of salt dissolved, the ionic strength is going to be high. If there's only a few ions, if there's not much salt, then the ionic strength is going to be low. And we don't have time in this class to go over the derivation of this limiting law, but we're going to talk about its effects, and we're going to talk about when it fails and why it fails a little bit. Hopefully, when you guys get the chance, you'll go study it a little bit on your own. Sorry, these notes didn't come out so well, but here I was just kind of demonstrating that when you have ions in solution, they're solvated, and so this is a negative ion surrounded by water molecules. It's a positive ion, and I'm showing you've got a force that's exerted between the two. We've got that limiting value of the Bai-Huckel law. A couple of things to note: that gamma plus minus goes as 10 to the negative of whatever that term is, right? And so it becomes smaller. Gamma plus minus, that is, the average activity coefficient, becomes smaller the larger the charges are. We've got that term z plus times z minus. As the z's grow in magnitude, the amount of force that those ions feel between each other in solution increases, right? And that force is going to lower the chemical potential. Therefore, it would need to, or the magnitude of the charge effect shows that as charges go up, the activity coefficient goes down, which indicates that the chemical potential drops, right? Was that too fast? This is why I have it recorded, so you can press rewind and listen to what I said again and see if it makes sense the second time through. So basically, the larger the charges are, the larger that negative thing is that we're going to raise 10 to. You raise 10 to a negative thing and it starts to drop down. It becomes a small thing, right? 10 to the negative 1 is 1/10, etc. 10 to the negative 2 is 1/100th. Essentially, gamma, the average activity coefficient, becomes larger the larger the magnitude of those charges are. And that's basically saying because the size of the charge dictates how much, how strongly those ions bind each other in solution. It also affects the chemical potential. It lowers chemical potential. Ionic strength, the I squared. So I give you a, there's an equation here, and basically what it says is, can't even read it. It's ionic strength is equal to the sum of the Z component raised to the power of its coefficient divided by the concentration, not, oh, I'm not getting this wrong, but this thing that's sitting here in a blur says that I is equal to 1/2 times the sum of the charge to coefficient times conc over C naught. I think that's the ionic strength. The ionic strength is a measure of how many other ions are in solution. And you see that in our equation for the limiting law, the ionic strength decreases the magnitude. As ionic strength grows in size, the magnitude of gamma plus minus is going to decrease, right? The larger that ionic strength is, the larger the negative log that you raise 10 to, so therefore the smaller gamma plus minus. In this equation, what that's trying to say is that the more concentrated a solution is, you got something that's kind of weakly concentrated versus something that is highly concentrated. And the more highly concentrated system, you're going to end up having more ions around you in general to feel electrostatic forces from, or to feel electronic push or pull. And so with higher ionic strength, you end up going to a lower chemical potential. And so you see that I to the 1/2, the larger that ionic strength becomes, the lower gamma plus minus becomes. This is not absolutely true. We talked about this. We said that when systems are kind of dilute, because there aren't a lot of ions around, the magnitude of forces felt between ions is kind of small, but that as the system grows in concentration, you get more ions around. The strengths of these forces increase as the concentration of ions around you increases. But we said that eventually you get so many ions around you that there are other effects in that solution that make it unfavorable to have an ion in solution. And so the way that I tried to say that say it again, I think there's a picture of it in a second. But the way that I drew that for you was I showed a graph of chemical potential versus conc of the ions. And I said that the chemical potential lowers from some initial value as you begin increasing the concentration of ions, but then as you get